Hey everybody, we're going to be doing some Chemistry 12 today, but before we do that, we're going to do a little bit of Chemistry 11 review. So we're going to be looking at three big things for our Chemistry 11 review. The first one is going to be a review on significant figures. What are they and how to work with them. The second thing we're going to be doing is calculating molar mass. So how many grams, are in 1 mole of a substance. And the final thing we'll be looking at is stoichiometry. So if we have a balanced equation, we can figure out how many products are formed based on the amount of reactants that we have. Okay, let's get started. So the first one that we're going to be looking at is significant figures. A significant figure is a number that is a measured number. So an example of this is something like 35.4 milliliters of water was measured. So volume can be a measured unit, mass can be a measured unit, and even if you were to count the amount of particles in a substance, that can also be a measured number, since the numbers are usually so high that they're kind of estimates. Now this differs from something that has an exact number, that do not have a significant figure. So example of this is 3 students studied chemistry. So it's not 3.1 students, it's not 2.9 students, it's 3, exactly 3. Unlike the 35.4 milliliters of water, it's possible that it could be 35.41 or 35.42 milliliters of water. Okay, that's very possible, but having 3.01 students is not possible. It's an exact number. So let's look at how many significant figures are in these examples right here. And what we see is we have a number like this, which is 12,000. 12,000 has 2 significant figures, this one and this one. Now these zeros are what we call insignificant because they are trailing zeros. Now we often use this in common English. We use zeros as insignificant numbers. If we find, like, an example would be a fossil, and we said that fossil is 65 million years old. Okay, so the 6 and the 5 are significant, and then all of those other zeros are insignificant figures. Okay, so getting back to this one right here, which is 12,000, we have 2 numbers that are important, and these 3 are insignificant. So this would have 2 sig figs. Now, something like this number right here, where you have a whole bunch of these leading zeros, 1, 2, 3, 4 leading zeros in between the decimal place and this number 2 right here, these are also insignificant. Okay, these are the only 2 important numbers. So we're unsure of this number that's way back here, so we didn't write it in. So the significant numbers here are this one and this one. So again, we have 2 sig figs. Now let's look at this next example. We have 3.01 times 10 to the minus 5. This number is significant, this number is significant, and this number is significant. This whole part down here is insignificant, so what we have here is 3 sig figs. Anytime you get a number with scientific notation and you need to calculate the number of sig figs it has, you can just ignore the times 10 to the whatever power it may be. Finally, we have, or not quite finally, but this number 100.00, we see that it's 1, 2, 3, 4, 5. Now these look like trailing zeros and they look insignificant, but in common language, if we were to say it's 100.00, it means that we are pretty certain that these are accurate numbers. These zeros here are accurate numbers. So this is significant, this is significant, 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 and significant. So we have 1, 2, 3, 4, 5 significant figures right here. Okay, So it's a little bit different. Now we have another one right here, so with some zeros in between, and then we also have another trailing zero. So we have 1 is a significant number. Now these ones are also significant numbers. Okay. Now we have this 0 at the end, but this is a little bit of an exception. If we have a decimal place right at the end, this is just signifying that everything that is ahead of it is significant. So this is also significant. So please remember, if you see a decimal point right there, everything to the left of it is significant. So we add these up: 1, 2, 3, 4, 5, 6 significant figures. Okay, let's move on. Okay, so now we're going to learn how to do working with a few significant numbers, or sig figs. So the first rule that we're going to learn about is the multiply and divide rule. Now this is a fairly easy rule. The multiply and divide rule says that the answer will have the least number of sig figs that are in the calculation. So again, the first thing we should do is calculate how many sig figs are in this first question right here. So we have 22.4. So all three of these numbers are significant. So this has 3 sig figs, is 22.4, and 1.2 has 2 sig figs. Okay, so if we just type into our calculator 22.4 times 1.2, what we should get is 26.88. Now we have 3 sig figs times 2 sig figs, and so what our final answer should be is 2 sig figs. Now what we have here is 4 sig figs, so this isn't working for us. We need to change this 26.88 into 2 significant figures. So we're going to change this into 2 sig figs. We're going to make it 27. Okay, so this is our actual answer, and we're going to just write it just like that. Okay, so now it is 2 sig figs. So right here we now have, for our next problem, we have again 2 sig figs times 2 sig figs. Okay, so 5.0 times 2.0, well, 5 times 2, as we know, is 10. Okay, now this is 2 sig figs, this is 2 sig figs. Our answer right here is only 1 sig fig. We need to change this 1 sig fig answer into a 2 sig fig answer. So we can do this by writing, again, 10, and we can do it one of 2 ways. We can write 10 and then write the point right there, or what we can do is put it into scientific notation and go 1.0 times 10 to the 1. Okay, so again, this is 2 sig figs, this is 2 sig figs, so both answers are acceptable. Okay, now the multiply and divide rule applies for both multiplication and division. So again, if we have, for this next problem, we see is 15 divided by 3.0. 15 is 2 sig figs divided by 2 sig figs. So our answer needs to be 2 sig figs. So 15 divided by 3, as we know, is 5. Now 5 is, again, 1 significant figure. So we need to change 1 significant figure into 2 significant figures. And we just add 5.0. Okay, so those are our 3 answers for these 3 problems right here. Let's move on and now talk about, instead of the multiply and divide rule, let's talk about the adding and subtracting rule. So here we have the adding and subtracting rule. Now, I have listed how this rule really works. So the first part is you need to round off the answer to the highest significant figure. Or what I like to do is I like to draw a line of significance. Okay, and I'll explain this, what this line of significance actually means. So even though this has 3 sig figs and 3 sig figs, it doesn't actually matter how many sig figs the parts in the question have. What is the really important thing is this line of significance. So I'm going to draw a line of significance right here. So I see that 12.0 here is my highest significant figure, and this has 2 decimal places, this has 1 decimal place, so my highest sig fig is right there. So I draw that, and then I just add it like I normally would, which would be 12.0 plus 3 is 15.0, and then this part would be, well, 5. Okay. Now, on this side of the line is insignificant. And this side of the line is what we want. This is what we keep, because all on this side of the line is significant. Okay, so since this is on this side of the line, we keep it. We keep the 1, 5, and the 0. This is insignificant. We don't keep this. But since this is above halfway, this is that 5, we round it to the next number. So this is going to be 15.1. And that's our answer, is 15.1. Okay, now what we do for this next one, which is 22,000 plus 400, we just kind of make a mark on what is significant. So this 2 is significant, this 2 is significant, and this 4 is significant. Everything else here is insignificant. So these 3 trailing zeros and these 2 trailing zeros are insignificant. Again, I'm going to draw my line of significance right here behind the 2, which is my highest significant figure, and right like that. So and then I just add it up like I normally would. So 22,400. Again, everything on this line, everything on this side of this line is insignificant. Everything on this line we want to keep. So 22,400, well, this is below halfway, so it just becomes 22,000. And that's actually the answer. So 22,000 plus 400, 400 is just insignificant, and so 22,000 plus 400 just equals 22,000. No change. Okay. Now, our next one right here, again, we have, this is a significant number, significant number, significant, significant, and significant. So this is our where we want to draw our line of significance right here. So we're just going to go ahead and draw it. We draw our line of significance, and then we just subtract this like we just normally would. So 22 minus 15 equals 7. Okay, and this is going to be 0.0. Now, what we see here is that even though this is 2 sig figs and this is 3 sig figs, everything on this line is insignificant. Okay, our answer only has 1 sig fig. Okay, and that is completely fine. It is not the multiplying dividing rule, it's the adding subtracting rule. So having 1 sig fig is completely fine, even if this is 2 and this is 3. So 7 is our answer. So 7.0 is technically wrong, just 7. Now, here is a little bit of a different one. We see 8.1 times 10 to the minus 3, and we're going to add it with 1.1 times 10 to the minus 2. So our scientific notation is not quite the same. So if we're going to add this up, we should make our scientific notation the same. So I'm going to change 8.1 times 10 to the minus 3, and I'm going to change that to 0.81 times 10 to the minus 2, and then I'm going to keep this number the same. So I'm going to keep this as 1.1 times 10 to the minus 2. Okay, so now that I'm adding it up, this is going to stay the same, times 10 to the minus 2, and I just add this straight up. But before I add this up, just like all my other questions, I'm going to draw my line of significance. So I draw my line of significance right just like that, and I then add it up. So 1.91. Now again, everything on this side is insignificant, everything on this side is significant. So my final answer is 1.9 times 10 to the minus 2. Okay, so then that's the adding subtracting rule. Moving on. Okay, now that we have significant figures down, we're going to talk about calculating molar mass. So if you remember from grade 11, here is a small section of the periodic table. We just have a few elements, the elements that we need to calculate the molar mass of these two examples right here. So we see that we have NH42SO4, okay, or in other words ammonium sulfate. And what we're going to do is we're going to calculate how many nitrogens we have here. So we have, it looks like we have one nitrogen, but on the outside of the brackets there's this 2 right here. So that means there's going to be 2 nitrogens, 2 times 4 hydrogens, so in other words 8 hydrogens, 1 sulfur, and 4 oxygens. So if we look on our periodic table, we see there's 14 nitrogens, there's 14 grams in 1 mole of nitrogen. So it's going to be, for nitrogen right here, it's going to be 14.0, and there's 2. Okay, so times 2. Now this one, there's 4 hydrogens here. Hydrogen has a molar mass of 1.0, so 1.0, and this is going to be 4 times 2, so that's going to be times by 8. Okay. Now, how many sulfurs are there? Well, there's only 1, and so it's going to be 32.1 times 1, or in other words, just 32.1. And then finally, we see oxygen. And we have 4 oxygen. Each oxygen has a molar mass of 16, so it's going to be 16.0 times by 4. Okay, so we're going to take all of these and add them up. Okay, and once we do that, we add all of these up, and we should get a number like 132.1 grams per mole. Now, remember that this 4, 2, and the 4 are exact numbers. It's not 4.1 are hydrogens for every 1 ammonium, or in other words 4 times 2, or 8.1 hydrogens, or there's not 4.1 or 3.9 oxygens. It's exactly 4 oxygens in one of these molecules. Okay, so those are exact numbers. Now, all of these other numbers right here, well, we're not actually 14 times 2, we're 14 plus 14.0 plus another 14.0. So if you do all of that and you keep your sig figs, you should always get 1 decimal place, because everything on our periodic table has just 1 decimal place. Okay, so our final answer is 132.1. Now let's take a look at this next question right here. Again, we have carbon, Okay, and that has a molar mass of 12. And we happen to have 12 carbons. Okay, and then we also have hydrogen, which has a molar mass of 1.0, and we have quite a few of them. We have 22. And we have oxygen, which has a molar mass of 16. Okay, and if we do this, this is going to be 144.0, and this is 22.0, and the final one is going to be 176.0. Okay, and if we add all of these numbers up, what we should get is 342.0. We need to keep those significant figures. Okay, grams per mole. Okay, so I did two slightly different variations on how to calculate the same thing. Okay then, so that's how to calculate molar mass. Moving on. To stoichiometry. So stoichiometry is the relationship between the amount of reactants used and the amount of products produced in a chemical reaction. So what we see is a formula right here of ammonia plus oxygen gas, and it makes water plus nitrogen monoxide. So the first thing you need to do, and it's very, very important in stoichiometry, is balance the equation. So right here we're going to balance the equation super quick, and what we see is that it's all balanced for us now. So there's 4 ammonium for every 5 oxygen gas, and that makes 6 waters and 4 nitrogen monoxides. So let's look at what we would get if we had 12 grams of nitrogen monoxide and was produced, and how many liters of oxygen gas was used at STP. Remember what STP is? Standard temperature and pressure. Okay, which is the standard temperature is 0 degrees Celsius, and the standard pressure is 101.3 kilopascals. Now, let's start doing a quick calculation here. So, the first thing we do is write down what we know, which happens to be 12.0 grams of nitrogen monoxide. Now, that is a number that we need to change into moles. So I'm going to change 12.0 grams of nitrogen monoxide into a number of moles, and the molar mass of nitrogen monoxide happens to be, well, 16 plus 14, which equals 30.0 grams. Now I write it this way, 30.0 grams is underneath the 1 mole, so my grams will cancel and I'll just be left with moles of nitrogen monoxide. I'm then going to use this ratio that we came up with from balancing this equation, and what we see is that for 4 nitrogen monoxides we have 5 oxygens. So we have a 5-to-4 ratio. So we did this so nitrogen monoxide can divide by nitrogen monoxide, and this is like a unit, it'll cancel. So now after this calculation, the unit that we'll have is moles of oxygen gas. Okay? Now, it says how many liters of oxygen gas was produced. And if you remember from your Chemistry 11 that in 1 mole at STP there is 22.4 liters of gas. Doesn't matter what kind of gas it is, as long as it's at STP there will be 22.4 liters of gas, and that'll be in 1 mole. Okay. Now, after doing this calculation, well, just to make sure, we have 3 sig figs, 3 sig figs. This is an exact number, 3 sig figs. Our answer will have also 3 sig figs. And so our answer turns out to be 11.2 liters of oxygen gas. Okay, so correct number of sig figs. Now, let's move on to the next problem right here. We see if we have 4.5 grams of ammonia, NH3, is used, then how many particles of water was made? So, again, write down what we know. 4.5 grams of ammonia. Now, the first thing I always do when I'm doing my stoichiometry is pretty much change it to moles. So I'm going to change it to moles. So 1 mole and is equal to the molar mass of ammonia, which is 14 plus 3 is 17.0 grams. And I'm going to multiply this by our ratio of 6 water, because that's what we want to find out, 6 water, and that is equal to 4 ammonia. Okay, so right now our unit is moles of water. Now, in 1 mole of water, or in 1 mole of anything, there is 6.02 times 10 to the 23 particles. Okay, and that's going to equal 2.39 times 10 to the 23 particles of oxygen, or sorry, of H2O. Okay, now let's go back over our answer, and we see we have 3 sig figs, an exact number, 3 sig figs, and 2 sig figs. So since this says 2 sig figs, our final answer should have 2 sig figs. And our final answer right now currently has 3 sig figs. So we need to change 2.39 to 2 sig figs. So in other words, it should become 2.4 times 10 to the 23 particles of H2O. And I always like to box in my answers. Okay, so if we're just going back over our answer, we just want to make sure that our units and everything else is correct. So I have grams divided by grams, and that forces these two things to cancel out. NH3 will also cancel out with NH3. Moles will cancel out with moles. And what we're left with is particles of H2O, and our final unit is particles of H2O. And that's what the question is asking for, particles of water. Same thing for this question. Your mass, cancel your mass, your nitrogen monoxide cancels the nitrogen monoxide, moles cancels with moles, and what you're left with is liters of oxygen gas. Liters of oxygen gas. Okay? So make sure all your units cancel and that you have the correct number of sig figs. So As you can see from the last two ones that we did, I always use what is called the mole bridge. So if I'm given a mass, a volume, or an amount of particles, I will immediately change that into the amount of moles. And from there, I can use mole ratio. The example was that 6 water to the 4 ammonia. And I can use that ratio to change it from moles of one type of molecule into moles of a different type of a molecule. And from there, it's fairly simple to change that back into a mass, a volume, or particles. So I can do mass, change it to moles, and go to a different species and change it into particles, okay, or pretty much any kind of thing. Now, let's look at something like molarity. If you remember from Chemistry 11, molarity is the concentration of a fluid. Molarity is often expressed as moles per liter. So here we have an example of a mass of salt or sodium chloride that is dissolved in some water, or in other words 550 milliliters, and we're asked what is the concentration of this. So we know what we need. We want the concentration, which the concentration is moles per liter, so we need to change 11.2 grams in 550 milliliters of water into moles per liter. So let's start off with the 11.2 grams. So we're going to take 11.2 grams of NaCl, and we're going to change this into moles. So we're going to times this by 1 mole is equal to, and then the molar mass of NaCl, which happens to be 23.0 plus 35.5, which equals 58.5 grams. So now the unit that we have is moles, because our grams cancels and we're left with moles of NaCl. Now what we need is moles per liter, so we're going to take that moles of NaCl and divide by the amount of liters. So 550.0 milliliters is equal to 0.5500 liters. And if we do this, 11.2 divided by 58.5 divided by 0.5500, what we will get is 0.348. And the unit for molarity is big M. Or sometimes you can just write moles over liters. Okay. Again, 3 sig figs, 3 sig figs, and 4 sig figs. Our answer is 3 sig figs. Now let's look at a different type of question of molarity, and look at the question of what happens if we have a certain concentration or a certain molarity of HCl in this case, and water is added. So what we're doing is we're diluting it. So what we're going to do is, the first thing, just like using that mole bridge of ours, we're going to change this concentration of HCl into moles. So we're going to take 0.25, and that's the other unit. Instead of having big M for molarity, we can also write moles per liter, and we're going to multiply this by the initial amount of liters that we have. In this case it's 45 milliliters, and we're just going to change that right away into liters, which happens to be 0.0450 liters. Now the unit that we have here, since liters cancels, we have moles of HCl. Now, what we're going to do with this is we're going to divide this by our new volume. So we're going to take 45.0 milliliters and add that to our 21.8 milliliters because we're adding some water, and that's going to equal 66.8 milliliters. But I'm going to change that to liters, so it's going to be 0.0668 liters. Okay, we do this quick calculation of 0.25 times this number divided by this number, and what we get is 0.17. Okay, 2 sig figs, 3 sig figs, and 3 sig figs. So our final answer is in 2 sig figs. Okay, and that's what our answer is. Okay, let's do a little bit harder. Now, last time we saw that we had we're diluting something. Now let's see what happens when we mix one concentration of something with another concentration. So we're taking 25 milliliters of 0.85 molar potassium hydroxide, and we're mixing it with 32.5 milliliters of 0.23 molar also potassium hydroxide. So what is the new concentration? Before we start on this, we should realize what the answer should be approximately. So what the answer should be is, well, it should be between these two numbers. So we're taking a strong concentration and a weak concentration, okay, or a concentrated amount of KOH and a dilute amount of KOH, and if we mix these two, what we should get is something that is in between. So we should get a number that is in between 0.85 and 0.23. So you should make sure to realize that before you start the problem, that your number should be in between those two numbers right there. So again, first thing I'm going to do is change everything into moles. So I'm going to take 0.85 moles per liter of KOH, and I'm going to times this by the amount of liters of this KOH right here, which happens to be 0.0250 liters. Okay, so right now I have moles of KOH, and more specifically I have moles of KOH in this volume right here. And what we're doing is that we're mixing it, or we're adding it to this amount, and I'm going to change this into moles as well. So I'm going to take 0.23 moles per liter, and I'm going to multiply this by the amount of liters. Okay, so again, let's go over it again really quickly. So what we see here is I'm taking this and liters cancels, so I have moles of KOH that I'm adding to moles of KOH. So I'm just adding moles to moles. Now, I want to have a concentration, so what I need to do is, well, concentration is measured in moles per liter, so I need to divide this by the number of liters, and the amount of liters that I'm going to have is 25.0 milliliters plus 32.5, which is going to be 57.5 milliliters, or making that into liters, it's going to be 0.0575 liters. Okay? And after all this is done, you're going to end up with 2 sig figs, and it's going to be 0.50 of KOH. Okay. So again, 0.50 molar of KOH, and that's our final answer right here. So now that we've done our Chemistry 11 review, I want you to do a few practice